Hello students, welcome again. Now we are entering the topic 5, and this topic 5 deals with your electromagnetic induction. Now this electromagnetic induction is a very interesting and very important concept also, because the principle that you are studying here, you will apply it for the electric generator as well as for a transformer also. So what are the subtopics that are discussed under this electromagnetic induction? That is, what is an electromagnetic induction and what is the phenomena? Also the Faraday's law of electromagnetic induction. Then you will also understand an important law that is called as the Lenz's law, and you will be able to apply the Fleming's right hand rule also. Yes, in the case of electric motor, you have studied the Fleming's left hand rule and its application. This Fleming's right hand rule will be very useful to apply it for an electric generator. To know what, we will see that step by step. Now going forward, to understand this electromagnetic induction phenomena, you are being explained in a step by step manner. For example, if you wind an insulated copper wire on an insulating tube, say for example a plastic tube, and please remember that you are not connecting this copper wire to any cell or a battery, but rather you are connecting it to a galvanometer. Now what is a galvanometer will do? It can detect, okay, if there is any current in this particular coil, this galvanometer can detect that. Then you are bringing a bar magnet with its north pole facing the coil and you are moving towards it. Then the galvanometer needle will deflect towards one side, and then again if you take away the bar magnet, okay, there is a deflection in the galvanometer but in the opposite direction. And then instead of north pole, if you put the south pole and move towards, the galvanometer deflection is noted. At the same time, when you move away the bar magnet also, the deflection in the galvanometer gets reversed again, indicating that there is some current being induced, because the galvanometer is after all showing a deflection of the needle. So due to this movement of the bar magnet either towards the coil or away from the coil. Yes. Also, if you place two coils wound on an insulating material, say for example a plastic tube, one coil is connected to a battery and then other coil is not connected to any battery, but it is nearby to this. When you switch on the current here, the galvanometer is showing a deflection, and when you switch off, again there is a deflection but in the opposite direction in the coil 2, suggesting that when this particular coil is in the, and now when a current is passed, what will happen? A magnetic field is produced. When you switch on, there is a change from 0 to some maximum value. Similarly, when you switch off, there is a change from maximum to minimum value. The change is causing and producing an induced current in the other coil, and that is what leads us to the definition of electromagnetic induction. That is the process by which current can be induced in one conductor due to changing magnetic field of another conductor is called electromagnetic induction. Also, the Faraday's law of electromagnetic induction will say very clearly that the induced EMF, because of which there will be a current flow, that induced EMF produced in the coil depends on the relative motion between the coil and the bar magnet. If coil and magnet are kept simply side by side, no induced EMF or no induced current can be there. There should be some relative motion between the coil and the bar magnet. That is, the induced EMF depends on the rate of change of magnetic flux. So E proportional to d phi by dt. This D notation you will be using to indicate that small variations we are studying. That means in a very small interval, what kind of very small change in the magnetic flux will be there. At the same time, the induced EMF in the coil depends on the number of turns in it. It can be represented as E proportional to N. Greater the number of turns, greater will be the induced EMF. Then when you combine these two results, E proportional to d phi by dt and E proportional to n, you will be getting E is equal to minus n d phi by dt. Why this minus sign is kept, that will be explained by the Lenz's law, which states that, let us see and then try to understand that. What it states is that, suppose you are moving the magnet towards a coil. Now in the coil, whatever the induced EMF and hence the induced current is there, the direction will be in such a way that it will be opposing the change that it is causing, that induced EMF and current. So now you are moving the bar magnet with its north pole towards the coil, therefore that face of the coil will behave like a north pole, opposing this north pole movement towards it. And then again, using your right hand, you can know the, if you observe the direction of the current with the curling of your fingers, then the thumb will give you the direction of the magnetic field. Even if you are taking away the north pole also, then that face of the coil will behave like south pole, opposing its motion, because south will attract the north, opposing. You are trying to move this will attract towards that. And then again you can understand the direction of current by curling your fingers, then the thumb will give you the direction of the magnetic field. So same case, if you are moving a south pole and a north pole also, you can understand the variation. If a south pole is moved, how the behavior is there. If a north pole is moved, how a behavior is there. Again, don't forget to apply your hand positioning also. Then in order to know the direction of the induced current, okay, in order to know the direction of the induced current, we will be using the Fleming's right hand rule, whereby please stretch your fingers in a proper manner such that the angle between the central finger, the forefinger and the thumb is 90 degree between any two fingers. So when you stretch your fingers, like if the forefinger is going to point in the direction of the magnetic field and the thumb is going to be pointed in the direction of the movement of the conductor, then the central finger will give you the direction of the induced current. So this will be very helpful. Just try to contrast this with the Fleming's left hand rule also, then your understanding will be even more better. So what is the point? When the forefinger is aligned along the direction of the magnetic field, the thumb is aligned along the direction of movement of conductor, then the central finger will give you the direction of the induced current. So this way you can clearly understand about the electromagnetic induction concept, and then the Faraday's law of electromagnetic induction, Lenz's law, and also the Fleming's right hand rule. So happy learning and thank you.